So welcome to DASI Solutions presentation of Discovering SolidWorks Costing. My name is Darin DASI. I have been with DASI Solutions now for just over 20 years. A couple of my favorite accolades is there's a competition we do in SolidWorks World every year called Model Mania, and I've been privileged to have won that competition twice. And this year I was able to place third, while one of my colleagues, Sean Bentley, was able to win the competition worldwide. So very cool stuff going around at DASI Solutions. I've been married just about 20 years. Got a couple of beautiful girls and a bunch of chickens running around my place. And this year my kids started calling me the Treehouse Master because everything I do starts in SolidWorks, including my treehouse. So I've had various projects at home, but I'm the kind of guy who likes to make sure that things fit before I really start going full bore into something. So everything I do starts in SolidWorks. Now, this would be using Weldments technology. I used wood profiles for the Weldments, but it still gives you the cut list and the bill of materials essentially, so you can go to your favorite lumber store and grab your supplies. My last project that I've just completed was a basement bathroom project. This project here was also vetted in SolidWorks to make sure things fit properly. And of course, the results are indicative of the preparation that we put into things. So SolidWorks is a tool for a lot of different areas, but mainly when you want to find out that everything is going to work before you start to really get deep into things, test it in the CAD system. Make sure it fits, everything looks good, and then go forward. Today my goal is to answer three fundamental questions about SolidWorks costing. That is what, why, and how. So the questions are really, what is SolidWorks costing? So for those of you who have never experienced it, obviously we want to tell you what it's all about. For those of you who know what it is but aren't really sure why it's there, again, we want to really refer to exactly where this tool fits within your design scenarios. And then how does it actually work? I'll get into some live demonstrations on the different aspects and types of geometries that we can vet using our SolidWorks costing tools. So what is SolidWorks costing? Well, SolidWorks costing, simply put, is a cost estimation tool built directly into our CAD product. Now, it works on different types of manufactured parts, which we'll refer to later, but mainly it's testing what the part geometry is based on how you would manufacture that. So you can quickly and repeatedly get some very nice cost estimations on different geometries. Now, for designer, what this can do is it can allow you to make cost decisions earlier, essentially changing geometries, using different features, maybe eliminating a setup or two, and those all translate to cost savings. As a manufacturer, you might be a sheet metal producer. You might have a bunch of Haas CNC mills that you need to keep running. Well, this allows you to take geometries from outside sources, whether they're SolidWorks users or use another CAD system, and actually provide very accurate quotes. It's a process that every company does, but generally this is a very manual process, and from person to person or day to day, those quotes can be different. So that is what it's about. Now, it's taking your internal knowledge, the rules that you use when you create parts and the information that you have available to you as far as material costs and such, and it applies those to the CAD geometry. And again, that's whether it's a native file created in SolidWorks with full feature history or just simply imported geometry. Now, it is a little different depending on what seat of SolidWorks you have, but chances are all of you still or already have the ability to do part costing, and that's included in every SolidWorks professional license. To do assembly level costing, which is really nothing more than running each individual part's costing at the assembly level for a total run-up, you would need a SolidWorks premium seat currently to do that. But for those of you with professional, you can get away with individual part costing. Maybe just do the arithmetic at the end. However, for premium, you'll see that at the end, it is literally boiled down to a single button pick to encompass everything. Now, with those descriptions, you're probably already filling in the blanks here of why use SolidWorks costing. But for those of you that are still a little bit uncertain, let me get a little deeper into the circumstance. When we're talking about costing, we're talking about somebody's tribal knowledge of the company. Their task is to receive geometry, whether it be part prints or 3D, to look at them, knowing what they know about how your business functions, what machines you have, people, processes, and you take that tribal knowledge and you apply it to a part. Now, estimation is just that. You're looking at a part and using what you know or think you know, giving a close ballpark to your customer. The problem with estimation is the potential to undercut yourself, whether you're trying to be competitive, whether it's a simple mistake that you didn't see something and therefore didn't account it into your costs, or whether you're really, just taking the geometries and from day to day, maybe having different opinions on what you see. And we want to capture those in a way that every time you cost a part, it's given the exact same criteria, the exact same thought process, so to speak. And we do that by using templates. Now, the templates themselves we'll talk about shortly, but they're what we use to capture the particulars about your business, whether it's the types of machines that you have and their particular setups, the costs for each of those setups, run times, and so on. But it allows us to grab all of the known data, put it down on paper, and apply it time after time after time on new geometries. And what that should give you is a much more accountable, repeatable, and accurate cost estimation, regardless of the type of geometry you might be receiving at the time. The biggest part I feel about this, though, is time. Costing or estimation is a time-consuming and very manual process. And anytime we're talking about these types of circumstances, of course, time is money, and that's time that can be saved. But when things are tedious, they also become a circumstance where concentration can lapse. And when you get into these very manual and tedious operations, things get missed. In fact, it just simply happens. And it doesn't matter how many times you've done it, you want to err on the side of caution, and sometimes that can lose business because now you're overpriced. But then also you can undercut yourself and win a job that actually costs you money. So we want to gather things as precisely as possible, which can be refined over time by modifying your templates and being able to apply those instantly, saving a ton of time with the application of those values to each part. Now, what's great about this, and just like SolidWorks, if you change a part, you change an assembly, your drawings automatically update. Well, costing does the same thing. When you change the geometry, the costing values will update. If it sees a new feature, it's going to add a new operation. If it sees a feature is removed, it's going to save that from the part. So it is a very cool process that is updating constantly as your geometry changes. Now, you can also use your costing capabilities if you're a manufacturer to create and capture business opportunities. Now, I'm going to talk about this a little bit later. But there are new methods of communication amongst the SolidWorks community that allows you to tell people that you're out there and that you can bring business in by providing your information online. We'll go a little deeper shortly. All right, so the first two questions are pretty straightforward. Well, now I want to get into the particulars of exactly how SolidWorks Costing functions. Now, SolidWorks Costing is a pretty vast product, and again, it's built into SolidWorks Professional and Premium seats, but it's basically used to apply costing to different types of processes or different geometries. So when we're talking about these templates, templates are unique to the process. So whether you do sheet metal components, you're going to be accounting for things like bends, and cuts will be done probably with a different type of machine than would be on a milled or turned type of a part. And these templates will automatically apply based on the geometry that they see. So the parts that we allow currently are different machined components, and that could be milled or turned parts. We'll do a lathe part here in a little bit. Cast parts, which are a lot like plastic molded parts when it comes to the vetting that they do. Sheet metal components, which of course have sort of a dual life. They're a flat pattern where there's a lot of features that are produced, but then of course they then form up to 3D in a variety of methods. We want to capture each of those idiosyncrasies of a part. Now, weldment components, or multi-body components in general, which could be mixes of welded or structural members, sheet metal components, and machined components, frankly, can also be done. And that is a multi-body part. So not an assembly, not individual part files, but a single part file with multiple disjointed bodies. Works a lot like an assembly, but in this case, single part file. Plastic molded is really going to be more about the volume of the component, the process a little bit when it comes to cycle times. And then 3D printing, really more specific to each machine. Whether you're doing FDM or PolyJet, there are runtime costs that we know. There are features about that we specifically capture, and of course material utilization on any of these. And I can't stress enough, but whether it's imported or native geometry, we capture them all. Single parts or assemblies, once again, professional versus premium are the specifics. Now, no matter which level of SolidWorks you're at with those, reports can be generated with the click of a button. We provide templates that can be customized. They're simple word .dots, document templates, and you can modify those with your particular details and customize them for your look and feel. But they capture a lot about what you've done, and especially if you've made changes, comparing a baseline to a new version and showing what those changes happen to be across the board. The title of this slide really says it all. Everything we're doing here comes down to the accuracy or the lack thereof of your templates. Now we have some methods of capturing which would be more of a draft quality type of a thing, which gives you a good ballpark, but isn't really going down to the minutia of each type of feature and process. But when you really want to make this as hyper accurate as possible, it's all about the data that you put into the templates. Now, these templates contain a lot of things. The materials that you have on hand and in what form, because that's also used to choose how the costing is run on a particular piece of geometry. What machines you have, whether they be mills, their speed and feed ratios, or material removal rates as we refer to those in costing. And then run costs. What's their dollars per hour, both of the machine and maybe the operator on those. What your labor costs for that operator. Setup costs, pre and post processes, adding material to the machine, chucking it in a different direction for those different types of setups. Even custom operations, what it costs to zinc plate, to anodize, to deburr a part, all of those have value. And then the material removal rates. When we're dealing with our costing setups, we need to know what tools you have available, because we can't cost a part accurately if we don't know what drill sizes and what mill sizes are available. Those all feed directly into the geometry, and that geometry determines whether a hole can be drilled or whether it has to be roughed and finished milled because it doesn't conform to a standard drill size. Now, rules are also something in these templates. Basically, I refer to those as an if this then that type of a thing. So if you see a part is this geometry, then maybe add some material to the outside of it for stock processing. Or if you see a part of this shape, maybe we're going to go ahead and zinc plate that as a final process. But no matter what, these templates are pretty unique to each company because, again, they encompass the machines that you have on the shop floor and everything about those machines. Now, I want to look a little deeper into these templates, but I'm not going to go seriously deep into them in this session. And the reason is because I've already created a YouTube video that talks about exactly what you need to do to either set up a template from scratch, starting from a blank slate, or taking one of the ones SolidWorks provides and modifying that to your particular needs. Now, looking at the templates that are there is going to let you know what details are there. And sometimes it's more tedious to remove a lot of things that are already there than it is to build it up from scratch. But this video will go ahead and show you that. Now, you can either type down or copy down the link or take a quick screenshot, or just simply go to YouTube and search for DASI Solutions and Costing, and you'll find this video up there already to go currently. But what I want to do really quickly here is just hop into SolidWorks for a moment, because that's where we're going to go ahead and get a bunch of the details about our costing templates. Now, when we're inside of SolidWorks, over on your right-hand side is where our File Explorer is. And under your Evaluate tab at the top is where you would trigger initially your SolidWorks costing application. Now, when I go ahead and select that, what it will do is fly out the sidebar and bring you directly to the Costing tab. Now, through this tool, we have the ability to go ahead and launch a template editor. Frankly, that can be done in Windows also by going to your search bar and just simply typing the SolidWorks template editor or costing template editor. But essentially, when you go ahead and launch a template editor, it'll bring up this tool that allows you to modify these geometries, or these values, Right now, I'm looking at an assembly cost template. Now, the assembly cost template, like I said, facilitates the costing of all the subparts and components within this assembly. So it's a little different than what you see when I get a single part on screen. But what it's utilizing is a said template for sheet metal geometries and a said template for machined geometries, and those are already linked directly to it. When I'm looking a little bit more specifically at those types of geometries, I can also take a look at the minutia that I was showing on that previous slide. So it boils down to things like your currency, localization of these types of values, but mainly it gets into the types of materials that you have on hand. Now you can see on the left-hand side that we have different materials for different disciplines. So if you're doing machining, you want to capture all of the stock that you have on hand, the type of material, the class of that material, the actual name that you might use for that material, and then what that stock type happens to be. Now stock type is important because there's a difference between plate and block when it comes to this 6061 alloy. And that would be the same for any type of material. If the geometry fits plate, then it would go directly to those thicknesses. But if not, it might default to block, which would require a bit more material removal depending on how that geometry fits amongst that stock. But in many cases, block would come off of just a giant billet, which would have been maybe cut down to size initially. So again, there's a different set of rules that actually apply depending on the geometries that you're looking at. Now this falls through with machining all the way through the materials that you might use or again have on hand. If you get down into plastics, we're talking about whether you use hot runners or cold runners and then specific materials there as well. I've got a couple others that are a little bit more rich than the one we're looking at right now. But we also talk about the machines that you have on hand. Now you want to go ahead and list the machines that you have, what their capabilities are, and what their particular values happen to be, whether it happens to be speeds or dollars per hour, or even the time it takes to load and unload those machines, because time times dollars per hour always rolls down to specific values. Now there's an initial or an interesting little a detail that we also apply to this, and this has to do with these setup costs, and it's whether they apply to a single part or whether they're divided over the total quantity or total lot size. So when you can set up a machine in one direction and then amortize that cost over a series of components, of course the cost per part will drop as a result of that. So we want to be very specific when it comes to these types of details. So whether you've got machinings that are going to cut or mill, down here there's a little bit more when it comes to plastic injection molding or die cast. SolidWorks also ships with some pretty rich templates here. This would actually be the default machining template that you would get from SolidWorks. And what you're going to see out of this one is that our default machining template comes with a lot of materials. You also have a series of different machines, even examples of what a cut machine is going to look like, whether it's water, plasma, or laser. An end cutting machine, cut off, bandsaw type. The injection molding machine and its particular costs, once again, whether they're divided over the total quantities. Put a mold in the machine once and all of those parts are run with the same setup. And even with die cast, similar types of things. When you're talking about the operations that you do, this is where internally this becomes very specific to each company. So cut operations are simply going to be a cut length per second type of thing, but milling gets into our material removal rates. Now these would be, again, specifically talked about in that YouTube video I previously mentioned, so I'm not going to go terribly deep into it. But we want to capture these criteria as accurately as possible and for as many tools as you have available within your company. And that'll allow us to take the particular materials, the types of tool that you would use for that material, whether it's a rough or finish pass, and exactly what those values are for the material removal rate so we can narrow down to the most accurate type of costed part. Drill libraries indicate what you have in your tool crib. This will also give you values of feedback, whether you have holes that maybe don't match with the drill holes that you have, or the drill types that you have in your library. These are places that you might be able to save a lot of money by simply modifying a custom hole, which would be roughed and finished milled, down to a hole that can simply be created through a single drill operation. Now library features and things like that get down to the things that you might use repetitively. And whenever you can use something over and not reinvent the wheel, of course, that's always going to be a cost savings. So those are the features that we maybe give just a flat cost, and once they see them on the part, that cost is then applied. And then custom operations. These would be pre or post-process operations, whether you have to inspect the part or paint it, coat it, mill or drill. Any of these things can be added with a simple right click in the upper left-hand corner of the costing operations. Lastly is rules. Now rules are those if then do this types of things. So if you select a particular rule, this rule here basically says that if the diameter is greater than 25 millimeters, then convert those drilled holes to milled circular pockets. We don't really have big drills that size, but we are going to go ahead and hog that material out with a mill and finish operation. Drill sizes, we want to go ahead and take ones that are within a particular distance and go to the next smallest in the tool crib in this case, and so on and so forth. These are those types of things that are always applied within your business. So first I want to go ahead and show you a little bit about machined parts. Now, machined parts, again, are going to start off with either plate or block stock. So if the thickness happens to match the plate, it could just very well be a profile cut and then some milled and drilled operations and maybe a second setup like you see with the top part here where there's actually some tapped holes going in from the side. What you can also do are turned operations on the lathe. These are going to be OD and ID drilling, but they will also throw milling operations, as you'll see here for the slot that we have up there on the top. Like I said, library features are those repeatable things. You don't want to reinvent the wheel if you don't have to, and anything that we can reuse is just simply going to be a cost savings. The other operations that we would do would be those custom operations, pre and post, whether they're anodizing, heat treating, again, inspection, or other types of applications. So let's get into SolidWorks and talk a little bit specifically about some of these types of parts. So first I want to go ahead and pull up one of my milled components here. And with this milled component here, what we're going to see over in our cost estimation is as you pull up the geometry, it's going to go ahead and show you a few specifics and previews on screen. So if you want to go ahead and actually see what the stock values are going to look like, we can change those on screen and update what our costs are going to be. This part now jumps up a little bit because now we have a totally different type of input value for this particular part. We're adding a bunch of stock, we're adding a bunch of scrap as a result of that. Now if we can narrow this down to a little bit more specific value, that's where our part becomes much more refined for the particular size. Now at the top what happens is it automatically sees the type of method that we would use here, and there's a little bit of flexibility with this. Geometries like we see on the screen can be produced a variety of different ways, therefore the choices. So we could machine this part, which is most likely what's going to happen based on the material that was chosen, in this case steel. But you could also switch to a cast operation and see what the difference in those might be and maybe go a different route for that type of material. Either way, as we're doing things, we can go ahead and see how these changes are taking place. Now currently I'm going to go ahead and lock this as my baseline. So my $37 part here is going to be my initial starting point that everything else will be compared to. Now with that I have some flexibilities. There are pull down menus based on the materials that are in your costing templates, so this list is truncated based on only what is available. And then from there I could switch this up and say maybe what it's going to look like with aluminum alloy. Now aluminum's got a lot more cost per weight ratio here, so we're going to have the same geometries, but our part just went up a few dollars in the actual total cost. If we were to switch from a block type to a plate type, well, the plate type in this particular case is giving us a warning. It says the plate isn't thick enough for this particular part. In fact, if you roll this around a little bit, you can actually see that the geometry doesn't match. So this one defaulted to a block because of the thickness of the material that we had available to us. Some other inputs that are interesting down here really determine what types of processes we're going to use on some of the geometries that you see on the screen. So if we go over into our feature manager, you're going to see a variety of things here. We've got a bunch of setup costs, and in those particular setup costs, we're seeing directions of attack on this particular part. So whether it's a setup on a different machine that's going to go ahead and take care of these through holes, or whether it's a different direction based on the geometries coming in from, say, the side, for example. The milling operations are going to list specifically here based on what they saw. This happens to be a pocket. We've got some slotted cutouts, and by expanding each of these out, it even shows you the tool that's used for those. And in this case, the formula that was actually captured was the tool times the dollars per minute, and that all equated out to this feature costing just under $2.50 for the machine and the time that it takes. Hole operations are something that are automatically detected based on what you see here. Now, the drill sizes that match are going to be the ones that are going to work for us. But when you list any of these out here that maybe are pretty large, like right now we've got this particular size one, you can actually see that there's a warning here that says the drill sizes don't match. There's a couple of holes that actually refers to. Well, these are the type that I might go ahead and take after the fact and just simply and proactively switch those over to a mill operation. Now what that's going to do on my part is take it from the original values that we have to a different value just based on the type of machine and the way that new setup is now going to have to roll down for that particular feature. Now with something like that, let's just go ahead and trigger this a little bit so I can get another update here. See what kind of shapes we're getting changes on. And that might be one of those changes where maybe we didn't want to do that, but it wasn't finding the proper method for this. So this is actually going to become our new baseline because the methodologies there weren't going to be able to find the proper drill size in order to make that hole to the size we needed. So this is now what we're looking at. Now all of these values can change based on things like number of parts. When you have setups which are going to be spread across those setups, by changing the quantity of the parts that we have here, we might very well be able to lower the cost. Now in this case, just making a few more parts, I didn't have a lot of those setups that happen to be individual per part, so we've only dropped about $0.50 per part with this mass quantity. But those are the types of things that, again, based on the way your templates are set up, are going to approach that part in a different manner. A different milled part, for example, in this particular case, is going to come up with a whole series of different values. Now when you take a look at a part like this, it's got geometries in a lot of different places. And this part probably could have started as a casting. Got another example of that we'll show in just a little bit. But it does come up with a few features here that show as no cost values assigned. And those are the types of things that we can go ahead and change based on, again, the way the templates are going to create those. In this particular circumstance, my guess is that there wasn't a ball nose end mill that's going to fit that particular type of a radius. But in our particular case, we're not getting a whole lot of feedback from what that one is. The hole operations in this particular case really translate to one of the things I see here, which is a massive amount of setups on this part. We have 4 operational setups because things are coming in from different directions. When you have to mill the part in this case, we have to set it up in those particular directions. But what really stands out to me, and I don't know if you saw this initially, but I've got a part that's going to cost me $4,200 to go ahead and create. Now when I see something like this, of course, that's a red flag. Now that red flag could be because of the stock we chose as maybe depleted uranium, who knows? But what you also see down here is a hole operation that's costing the bulk of that $4,200 all on its own. And when you expand that out, what we're finding there is that there's, again, no drill size to match this. And in fact, it's defaulting to a 1mm drill. So with a part like this, of course, we're going to go ahead and take that feature and let's make that a milled feature instead. Now obviously what that does is it drops 93% of the cost of this part and drops it down to a little bit more reasonable $280 for this entire operation. Those are the kind of things that we want to make sure that we catch up front, or we don't misestimate, because that's where problems are going to happen between you and your customers. Turned parts are a little bit of a different story. Not much, they just have a different operation associated with those. Now with turned parts, what we do is we change it from block or plate to really simply cylindrical stock. Now I could go ahead and change this and make this part as a milled part, but I guarantee you that's not going to be the most efficient way to do this. So as a part that starts with cylindrical geometries, we end up with a component now that's going to be created through a series of turning operations. So what we have here is OD and ID grooving operations, and as you select those, you'll be able to visualize those on screen. What we also see are a series of hole operations, and those come from different setups. This part having 10 different setups, 5 of those being operational or positional setups. Each feature also nested specifically beneath those setups for convenience. But what we also see here is a milled operation, and that's the pocket that's going to come in from the top to take care of that key slot. Now by changing the stock, of course, we're going to go from a part that's about $129 now up to a part that's going to be a little more expensive based on the wasted material that we have here. But those are the types of flexibilities, once again, that you have, and the ability for you to go ahead and do some quick what-if scenarios if maybe you're dealing with a particular piece of stock that you do have available to you. Now for cast parts, this one here is interesting. What it's really doing is more like a plastic injection mold circumstances. It's analyzing the amount of material that you're using. So the cost per volume on the material is all equated to what the physical volume of the part happens to be. There are, however, other inputs. Those have to do with the cycle time specifically with this part. So the amount of time it takes to heat the mold, to inject, or to fill, both of those are kind of used synonymously together. The cooling wait time, and then the removal from the mold or the ejecting process. What you're really getting is the cost of materials plus that manufacturing time. So as we take a look at what we have on screen here for this particular part, let me just clean up a little bit and get rid of some of the other components that we have on screen here. I want to pull up this cast part and show really what the great features or details of this particular type of operation are. There we go. Another mounting plate that I would like to use. So this part here immediately comes up as a cast part, just simply again based on its geometry. When we're talking about a cast part, the details that we have are going to be cycle times. So how long does it take to fill, a cost of the mold, because the tool, of course, being amortized over how many parts you can get out of it is why plastic injection molding is such a coveted type of production process. Lost cast molding, lost sand casting or wax casting, those types are destructive processes where you're only going to get one part out of each individual mold. But you have the ability to go ahead and push those across and say what number of cavities you might actually want to have in there as well. So the molding operation on this particular part is the only thing that we're actually going to see, and the part itself is pretty efficient in price. However, this part also has its dual life, and that is in the form of a configuration. So I'm going to move over to a configuration now in this part that actually has machined features to it. When we take a look at this part, we're now looking at a part that's about $102. Now visually, that makes sense to me, and the reason it does is because of the preview that we have on the stock. Well, one thing we've added was the ability to take a part that's a known cast component and a known machine component of the cast and allow us to use that casting as our baseline stock body. So in this case, instead of raw materials, we're going to use a custom body type. Now we could actually look at a different part file. So for those customers out there that track a cast part and a machine part with two different part numbers, hence being two different files, you can go ahead and reference that other part and basically just use that as the stock body. In my case here, what I have is another configuration, which is that cast configuration. And by updating the stock body, I'll go from $102.05 down to a part that's much more reasonable. We'll click to update this and go ahead and see what that change is going to be. Because of the lack of scrap and much less machining as a result of what we now see on the screen, we're now going to get a part that is more reasonable once again down to $32. So all we really have are the hole operations that we're going to have on the top of the part in the 4-hole pattern, and then a couple of simple mill operations, and those happen to be for this bottom pocketing that we're taking off this part. So great accuracy when your parts don't start from stock off the shelf, but instead start from a pre-existing casting that just requires a few finished passes. Now, weldments are a multi-body component. When we're talking about multi-body specifically, we usually get into sheet metal and weldments as those two processes. But in reality, multi-body can be a mix of three main components, whether it be the sheet metal, the structural members of the weldments, and machined components, which in this case, we have a sheet metal top, could be sheet metal gussets, those could also be machined, and then we have these structural extruded members on the legs of this particular part. Now the way this one actually works is slightly different. Because we're not talking about an assembly, we can't really break open or open individual bodies in their own windows. But the interface here facilitates that particular operation. So let me wait for this to update. So with the multi-body process here, it's breaking down each individual body as if they were individual part files. So over on the left, you see that we have a dozen general bodies, a couple of welding operations, and those are in the form of either weld beads or fillet weld beads. And then there's the sheet metal body that it's actually detected for the top face of this particular part. Now this part's quite large. It's actually 1 meter tall and about 1.5 meters wide. So we get a lot of detail in these particular features. But like our assembly costing, which you'll see in a moment, we are using an overall template and then individual templates for the types of disciplines like machining and sheet metal below that. And that allows us to go ahead and take these components and choose the types of methods each of those gets used. Now it detects this automatically, but I do have the ability to grab these types of things and maybe change the type of body it is and the type of machining method I might use for each. So there's a tremendous amount of granular control for any of these types of features. Structural members are chosen as a structural member method, and this is going to give us a cost per unit length or per stock length. So when we begin cost estimation, it will now run it up on all 6 of the individual body types that we have here. And I say 6 because we have patterns. The legs are all the same, the gussets are all the same, and the end and side pieces are the same. So those don't have to be costed individually. Now what we get over here is an individual run-up on all the bodies. And if we take a look at the expansion of each of these, we start to see these different rectangular members. Now these long ones over here on the side are about 2 meters each. So we have a total of 4 meters of extruded metal in this case. And this happens to be, we'll go back and check it real quick, but plain carbon steel. Now with each of these, we're going to see the specifics of the bodies. And a double click on each of these bodies does allow us to jump into the details of each. So now what we'll see on screen is only one of the individual bodies that we've gone down to. It'll also show us the individual costing and how that's been run up as if we're looking at a single part file now. And it even gives us the individuality of the different cuts that are there. And these are just a couple of simple cutoffs. And then we have the material value, which is our main process. It's about $72 per meter for this particular material. Clicking this button here will get us back into either the assembly or the multi-part environment, depending on where we started. So every one of these is going to give us the specifics on the way it was run up. So here we're talking about something that's just under a meter, total of about 1.68 meters for these two side bodies here. And then those are about $71 per meter. And that's how our costs are arrived at. The sheet metal component, let's go ahead and take a look at that one on top. We'll break this one out on its own. And again, it will break it down to a different type of cost analysis. And in that case, it's going to give us things like cut operations, the machine that we use for the setup for this, which happens to be a laser, and then the two cut paths, the outside profile and the inside profile. Now, sheet metal parts are generally going to be deemed using, say, dollars per inch or dollars per millimeter when it comes to the speed and feed of a laser, a water jet, or a plasma cutter. Now, sort of a preview to assemblies. This is giving each individual body, but then running it up to a total cost for the entire multi-body part vis-a-vis the assembly that we're seeing currently. Once again, multi-body parts use 3 types of geometry disciplines: sheet metal, weldment, and machined types of parts. Plastic injection molded is much like what you saw with the cast materials as well. It has cycle times. Those are going to be dollars per hour when it comes to the machine itself. And efficiencies on hold time, pack time, and ejection time are really where the dollars can be saved implicitly on any type of plastic injection molded part. You want to walk that line as close as you can because it's also very close to having short shots or parts that don't cool and end up warping. So it's quite a bit of an art to set up machines like that. Now, when we're dealing with plastic injection molded parts, we also have a scrap value. Now, we have hot and cold runners. Hot runners would be heated throughout the actual mold and therefore not scrapped and thrown into regrind afterwards. But cold runners, if you switch to that, is going to increase the scrap cost, which of course is going to increase the cost per component based on how many have to be shot into the mold. Like I said, this is very much like you saw with the initial casting of the part. This happens to be, in this case, a multi-body solid once again, only it happens to be multi-body in the case of multiple plastic parts. We'll do a little explode view here so you can see the way this cap goes together, and each of those parts is going to be run up individually. So over to costing, it's going to see each of those parts, which I'm going to multi-select using Control, and the method we're going to use on that is going to be plastic. We'll go ahead and begin. So all the things you're seeing now are happening live. So the speed that you're seeing there is definitely real time. We're getting 3 bodies there. The cover here is about $53. This one's here about $53. This one's about $53. So generally they're near the same material and volume when it comes to the individuality of each of these parts. If we go ahead and take a look at this cover in its own window, we'll see the specifics of how this part's going to look once again and exactly what the mold operation is going to be used for this. We switch to cold runner. Again, we'll get a different type of material utilization and a scrap value associated with that. Now, there are some ways that we can maybe take this part, instead of it being plastic, maybe switch it to a 3D printed type of a part. A little preview of what we're going to do next. It'll take that part and it will lay it into the actual printing machine. The 3D printed template is going to actually contain the types of machines that you have available to you. So we go ahead and actually take a look at the operational costs or the setup costs. We can see on those types of things that there are different machines available to us. And I'll show you a different template that's going to have just a little bit more to it when it comes to the types of machines and operations that are available to us. But essentially, it's going to put the part in position and therefore give us $1 per hour on a machine like this. Now, any FDM machine that you might use is also going to have material costs when it comes to the spools and the resins that you happen to be using. But the position that that part is actually sitting in is also important. This is going to require a lot of support material that's positioned this way. So if we flip the direction of it and basically sit the part flat within the print volume, that's where we're going to go ahead and have the capabilities of maybe lowering the cost of a part like this. And as a 3D printed part, it drops down to $11. We'll go back into our total cost analysis, and if we decide to 3D print one part and plastic injection mold the rest, we're looking at an assembly that dropped about $35 on this. Now, this is one of those things where with plastic injection molding, the number of parts is definitely going to go ahead and affect the cost of any one of these things. So if we want to go ahead and take what we're currently at as a baseline, I want to show you that these $53 parts is because we were only making 100 of those on one particular mold. But if we now go ahead and take a look at any one of these parts on their own, this part now drops to $3.35 because doing 100,000 of them on a mold that costs 10 grand is definitely much more cost effective than doing only 100 parts on a mold that costs 10 grand. So those are the types of things that you can see right up front when it comes down to the specifics of how a part is produced and how that part's cost can be spread out over the life of the manufacturing method. Now, as I was doing that, I jumped a little bit forward into the 3D printed part, so we've really just covered this already. But it has to do with again, the material that's being used and the position that the material is being laid down on the machine, because there's other consumables that have to be considered when it comes to machine type and, of course, position of the geometry. Now, back to the actual part itself here for a second. Whenever we're looking at components like this, and I'm just going to go ahead and take any one of these parts and we'll go back in its own window for just 1 second here. We want to take this and just use a little bit of a different type of a machining template. I'm going to go back to one that's maybe just a little bit older when it comes to this particular part. And when I'm looking at this particular part here, let's go ahead and go to maybe the 2014 template on something like this. Here, 2015, one of these other ones I like. Yeah, it looks pretty good. This is again where you're going to be able to go ahead and modify the types of machines that are available for these particular processes. So for 3D printing, you might end up with, excuse me on this one. For 3D printing, you might end up with things like a MakerBot. Maybe you've got a Fortis or Dimension type of machine. And we're going to want to be able to account for the specific materials that are being used for each of those types of machines. Switching from a PolyJet to an FDM machine, obviously will have a drastic difference in the cost of that particular type of a part. Last but certainly not least, I wanted to circle back and talk a little bit more about a sheet metal component and how we approach each of those. Sheet metal parts are those parts that really have kind of a dual life. They work in a flat pattern. A lot of geometries are then lasered out in that flat pattern, and then the part goes through the forming or folding process to go to its 3D life. Now, if you have access to a very sophisticated and usually very expensive multi-axis laser, a lot of these things don't have to be considered in their flat pattern. But in real life, most people have a brake press of some sort and access to just basic cutting machines. So we want to be able to have both of these types of disciplines accounted for. So when we take a look back at a couple of the other parts that we're dealing with here, I'm going to use this part specifically. But with this one here, I want to go ahead and just simply run the analysis. And with sheet metal parts, we get a few other pieces of feedback. This one here is going to automatically do some blank analysis, or what we need for the entire outline of this part. Now, when we take a look at the actual cut path of this part, we've also got a rule on this one that's giving us a little bit of stock offset here so that we can nest multiple parts on a given stock of material. Now, sheet metal also has another method that allows us to either cost the part by a specific weight, so individual to the part, sort of on an island, or based on sheet size. So when you have a circumstance here where you actually have, and in some cases CNC benders will pull a 4x8 foot sheet of material off of the shelf, put it in the machine, and then nest as many parts as possible within this process. Now my part costs $12.82 right now, but if I switch the sheet size, what I'm getting is an increase in the price. And one of the reasons I know that is because when I'm taking a look at the actual use of the sheets, I can see that I have 68% scrap based on what I'm doing. And by looking at the bounding box on this, I can see that my first sheet is fully encompassed and there's a little bit of scrap at the end. But my last sheet, I'm actually going to lose a whole bunch of material. So if I go ahead and put, in this case, 14 more, and I'm only going to do 13 more just for fun, but if we go ahead and change the lot size on here and I go from 50 to 63, I can actually produce more parts and drop them down about $2 per part specifically, because now what we have is a much better utilization of our materials, and there we can see that we've now got less scrap as a result of that. Now that said, there's another part that I want to show here that actually encompasses that in a real nice way as well, and that's this part right here. When we take a look at the particular materials that we're going to use for this particular part, what I want to do is switch this over to a little bit more recent version of our costing templates so we can get some capabilities out of this. But what I see is a part that's about $8.57 currently. Now at this particular value, I can switch this from material weight over to sheet size. And sheet size will give me a little bit more or less cost per unit size. Now in something like this, I've got multiple sheet sizes available for stock, and those are going to then allow us to fit it a little bit more strategically within that area. But if we also go ahead and change the way the part is going to fit, I can see that this is a little bit more of an oblong type of a feature. And you can see right there, we've got a nice size fitting there. Now if I switch it up on my sheet, what you'll also see is maybe a little bit of a different type of a layout. You see how it's actually utilizing this and nesting that in a better format. Look at my last sheet here, maybe add a few hundred of those, and that's going to go ahead and fit on that sheet different, not in necessarily a specific direction, but in more of an optimized layout so that it utilizes our sheets a little bit more effectively. Part like this is also quite interesting because though it looks like sheet metal, has bends, you can see pretty plainly that there's also some other operations here. There are some countersunk drilled holes on this part, and actually there's a little bit of a slot on the back side of this. Now those are the types of things that actually can be defined in a different way than using our sheet metal templates. And actually in this case, we could define these using machined templates. Now because those features will be machined, this is more or less a mix of machining operations and sheet metal operations. But one of the things that we want to make sure we do is going into our setups is we just want to make sure that we've got the proper types of values for these operations. So here what we see is that we're going to be using a machining template for what we're doing, but we're applying a hard cost for these bends, hems, and library features, which are sheet metal processes. So in this case, we're actually going to be getting a mix over here. If you see mill operations, cut operations, and hole operations, well now we're going to actually have a mix of all of those. So there's the mill operations, and then now we have our bends at a particular hard-coded value for each of those. So this gives us the slot that's going to be milled off the back side of the part, the entire bottom face of this part that's going to have to be milled off as well, our hole operations, which are in our particular positions, which would be drilled off of our flat pattern, and then even some of these other operations, which are actually going to be just basic laser cut paths. You can see the outside profile, as well as these holes that are up on this particular face, previewed in the flat, but shown up here in the top. So this is a very good mixed life part that actually has machined and sheet metal features living harmoniously within the single type of geometry. Now I mentioned how to capture business, and capturing business is now starting to take place using mysolidworks.com. If you are a sheet metal manufacturer, you can choose your costing templates like we've been doing local, but you can now actually say use costing templates from mysolidworks.com. What's happening is that sheet metal manufacturers are doing their own costing internally. And using our costing template tools and being able to edit these templates, you can actually save these particular templates under the Save As something called a limited access copy. Now what that enables us to do is provide our templates to other users of SolidWorks so that they can apply them to their geometry, but they cannot open, edit, or see the details that we have built within our template. So manufacturers are building their templates to their own specs. They're putting them up on mysolidworks.com so that if you need sheet metal parts produced, you can get their templates, run them on your part, and it will tell you exactly how much these companies are going to charge you for their sheet metal manufacturing based on their own numbers. Now, if you're a sheet metal manufacturer, making a good template is great for your own purposes, but getting it out there to the SolidWorks community on mysolidworks.com will allow others to then funnel business towards you, because they're going to have a level of comfort up front that your values and your templates are going to be the costs that they actually have to pay. So it's a way that we can connect users and producers in the SolidWorks community alike, so that we can go ahead and get the best costs by driving business to those people who are best at it. Now, the last feature I want to show you here is assembly cost, and I don't need to dwell on this one too much because it really just takes all the individual disciplines and rolls them up into one operation. So back into SolidWorks for a moment here, we're going to go ahead and take a look at this top level assembly. Now, what it shows us over on the right hand side are what templates are going to be used. Those can be modified currently. It also shows us what parts have yet to be costed. So in this case, I'm midstream on that side part there, but that one's going to go ahead and be costed as a sheet metal part. This one over here on the side, also a sheet metal part, and then this one on the back, also a sheet metal part. But ones that we've already done are going to be things like that bracket up front. We have some purchased components. If you take a look down here, those purchased values are listed as hard-coded cost numbers within these components. And then if you happen to use Toolbox, you can also go ahead and apply hard-coded purchased values to each of these Toolbox components. And that will then give us quantity times their cost and add that into the total value as well. So using a mix of sheet metal, machined components, purchased components, and then Toolbox components, which would again be purchased, we simply go ahead and begin the cost estimation right here from the top. Now, this does require SolidWorks Premium, but you're really just seeing the conglomeration or the combining of every one of these disciplines into a single one source of costing. Runs up this entire assembly as being $284, and the result of that is that all of the individual components and their quantities then basically speak to that cost. So there's purchase parts, they're individuals, and then there are Toolbox parts and their particular quantities. So in this case, we have a 74-cent component times 4 gives us our total cost. Custom operations can be added either before and after. These are again on the template, so if I need to go ahead and assemble this thing at the end, we're going to do that to all parts. That's going to then run that cost right across each of those and then put that cost to be just a touch higher. Now, I'm going to come back to this slide in 1 second, because one of the things I really like to talk about is how we get this information out to your users. So in essence, that has to come down to what our results are. Now, the results can be disseminated to anybody, either inside or outside your organization, by simply clicking this button in the lower right-hand corner, which is to generate a report. Now, as I mentioned, we can go ahead and fill these things out with anything that we'd like. I'll just put a few details here just so it makes a little bit of sense and sort of looks nice on the screen. Get a few things down there. But essentially, by using the templates and clicking publish, it will take everything that we've done and it will throw it onto a simple Word document that we can share with anybody we'd like. Now, it's using a .dot file, which is completely customizable. You'll see on this one I've gone ahead and I've added my own logos and things to the interface. And I'm just waiting for Microsoft Word to pop up here on my taskbar with my brand new template report being generated. Now, these again are the tedious types of things. So here we have some information up front. We've got our customer art Vandalay, and then down here we have the assembly, which as a result of the additional assembly steps has actually increased the cost by a good percentage. But it also goes to show you the individual values of each component, whether purchased, machined, or sheet metal within this assembly, and again the total cost of each of those parts. Down a little bit further, you will see the calculated parts, the purchased, and the Toolbox components, and again each individual costs broken out for those types of components. And then finally on the last sheet, the total cost run up for this entire assembly times the quantity. So with all that, I hope it at least gave you a little taste of what SolidWorks Costing has to offer. Now, of course, we wanted to answer some questions, so hopefully you got the question of what SolidWorks Costing is. And it's really just a fast and repeatable cost estimation tool. We do a lot of different types of part geometries, but fast and repeatable are just going to simply save you money right off the bat. Now, why would we use this? Well, it just saves time, frankly. These types of things are mind-numbing, they are repetitive, and frankly, if you're the only person doing costing, that's going to be your job, no matter what. And this allows you to capture what you know in that tribal knowledge and really have anybody within your company apply it to the geometries that they're creating, either up front so they can make different decisions, or a little bit later in the process so we can just simply provide nice, simple, and repeatable types of cost estimations to our customers. For yourself, if you happen to be a sheet metal producer, you can place your templates in a read-only and very hidden format up on mysolidworks.com for other users out there to consume. And how? Well, you capture everything on templates. That's really the key to everything. Once you've got it on the template, the rest is very quick and automated. The reports will then take all the details that we've done, changes we've made, and the differences between the good and the bad of those changes, and it lays it out in an easy-to-use and distributable template that you can provide to basically anybody with a computer. So with that, I want to thank you for spending an hour with DASI Solutions discovering SolidWorks Costing. If you have any more questions, please don't hesitate to either get a hold of myself, and that's Darin at dasi-solutions.com, or any one of your sales representatives or account managers, or simply call tech support and let them know that you've got questions. And we'll be able to walk you through a lot of those processes as you're sitting right at your computer. So again, thank you very much for spending your time today. I really appreciate you spending a valuable hour with me. Get a hold of us if you have any other questions regarding SolidWorks Costing, or frankly, any of the other services that we provide. Thank you very much. Have a great day.